Okay, up next is comparing functions. In comparing functions, we want to compare apples to apples. So if we have maybe a verbal description or or a numeric, graphic, or symbolic, we want to compare them in that way. Okay, so verbal description, we can kind of qualitatively say, okay, this is increasing by 2, and then by 3, and then by 4. So this is kind of growing like a triangle. This one we're starting with 3, we're going to 5, and so this one's, it looks like we're growing by 2 each time. So we can compare those two and say that these functions are different. This one is growing not by a constant. This one is growing by constantly by 2 each time. So we can compare them in that way. The numeric, so I can also compare the rates of change here. So how is this changing? It's growing by adding 2, and then it's adding 3, and so on. This one, it's growing, let's see, its rate of change is adding 2 and adding 2. So I can compare them in that way. It's also helpful to look at where they would start. So what would it be at the 0 step? So if I work backwards, right, if I said at step 0, if I go backwards, I would take away 2, right? So minus 2, and then take away 2 from 3, I'd be at 1, right? So if you look at this, I'm taking away 2 from 7, I get to 5. Take away 2, I get to 3. So if I take away 2 from this, I would be at 1, right? So that's kind of another important point is your starting point or your initial condition. What would happen here? Let's see if I took away 3, then took away 2, then took away 1, I'd be at 0, right? So this would be 0, 0. So I would have nothing there, right? And then there are graphs. So you could graph these on kind of an XY plane. So this first point that we got was 1, 1, and then it was 2, 3, and 3, 6. And then if I wanted to put my 0, 0 in there, it looks like that. So this one kind of grows at a different rate. So it's growing by 1, then by 2, then by 3. So plus 3, plus 2, plus 1. And over here, it's growing by 2 each time, right? Plus 2, plus 2. And then if I went back to, I'd be at that point, right? Which is what I expect at 0, comma 1. There would also be a point, right? So this is 0, comma 1, kind of my initial condition, the starting condition. And this was 1, comma 3, and so on. Okay, so there are these different representations we can look at and say that, you know, this one's growing at a different rate than this one. Now finally the symbolic. This one kind of has the most power because you can predict way out in the future where this graph is going to go. So if I say at the 100th step, where is it going to be? So I just plug in 100 for n, and I can find that out. So the way that you make this system, so this is a linear, so this has a constant rate of change. If it's constantly changing, plus 2, plus 2, plus 2, well, that's the same as repeatedly adding 2, right? So repeatedly adding 2 is the same as multiplying by 2, right? So if I had 2 plus 2, that's the same as 2 times 2, right? And if I had 2 plus 2 plus 2, that's the same as 2 times 3, right? So it's 2 times whatever number of times you're adding the 2. So if I was to add it 0 times, it'd be 2 times 0 plus 1, which would give me this first point, right? Or this 0 step, right? Or if I wanted to find out, okay, 2 times 1, so the first step, 2 times 1, which is 2, plus 1, I get 3, which gives me that one. So you have these two points, or 2 bits of information that come in a linear function. You have your multiplier, and you have your initial condition. So when n is equal to 0, that is your point. And then whatever you're repeatedly adding, that is your multiplier on the variable. Okay, so that's the way you can pick those two out. This one's a little bit more difficult to come up with, so I just kind of I gave it to you. But if you want to think about, this is n times n plus 1 divided by 2, uh, you can kind of think of this as, this is a rectangle. If I doubled it, right, and this side length would be n, and this side length would be n plus 1. So if I find the area of this rectangle, it would be n times n plus 1, but it's only half of that rectangle, right? So that's why we divide by 2. So this is kind of more of a geometric type of problem. We'll get into that a little bit later in the course, but don't worry too much about it. So it's a special triangle function that we like to use as well. Okay, so let's compare a couple of functions. So is this the same as this, right? Well, the way I can do that is I want to compare apples to apples. Either I want to get a graph of this, or I want to get a table of values of this and see if they're the same. And I also want to compare which one is increasing faster or decreasing, decreasing faster. Is this one decreasing at a certain rate and this one's decreasing at a faster rate or a slower rate, or maybe it's going even increasing at some rate. Alright, so let's make a table of values for this one. So this would be at step 1, it's 4, at step 2, it's 3.5, at step 3, it's 3, and step 4, it's 2.5. Alright, so I can tell right now that these are not the same function, right? What is the rate of change? So it looks like here it actually decreased by 1/2, so this is minus 1/2, and here it's also taking away 1/2. So it looks like this is a linear function, minus 1/2 each time. So the multiplier is minus 1/2. So if I were to write the symbolic form of this, it would be minus 1/2 times n, and then I want to find my initial condition. So I have to actually go back a step to step 0. So if I were subtracting 1/2 each time, to go back, I would have to add 1/2 to 4, so it would be 4.5. So this is plus 4.5 would be the symbolic representation of this graph. Okay, and let's compare this one. Let's make a graph of this. So 1, 2, 3, 4, 5. There'd be a point right there, and then 2, 4, and 3, 3, and 2, or 4, 2, and it looks to be going in a linear path going down. So how is this changing? Let's see, it's going down by 1, and down by 1, and down by 1. So it is a constant rate of change. So this is also a linear function. And if I want to find my 0 point, my initial condition, I need to go back. So instead of subtracting 1, I'm adding 1 each time, right? 1, 1, 1. So I go to 0, 6 would be my initial condition. Alright, so I can make my symbolic representation. It would be, let's see, the multiplier is negative 1. So negative 1 times n, and my initial condition is 6. So I can check those values. Let's check 3, for example. So if I put in negative 1 times 3 is negative 3. Negative 3 plus 6 would be 3. So it checks out. You probably won't see this as negative 1 times n. You'd probably just see it as negative n plus 6. Or you could even switch the order and say it's 6 minus n. You can see all of these different forms. They are all equivalent. So I'll just say that's my example. So which one is increasing faster or decreasing faster? So you want to compare the multiplier, right? So this one's decreasing faster, isn't it? It's going down faster than this one. So we say this is decreasing, decreasing, I guess, faster. Because it's going down by negative 1 each time. This one's going down by 1/2. So you can compare those that way. If you have some increasing, so it's the steeper line, right, is going to be increasing faster. So this would have a rate of change that might be, it would be a smaller number than this rate of change, right? So for every 1, this one's going up a little bit, and for every 1, this one's going up more. So you can compare them in that way. You could say this one is increasing faster than this one. So just to throw some numbers on it, say this is going up by, I don't know, 1/2, and this one's going up by 3 for every 1 or something. So this one's going up by 1/2, and this one's going up by 3 or something like that. Okay, so that's what you're going to do on the next part of the assignment.